Hello everyone, my name is Mriganko Biswas. I am from EEE Department, India Institute of Technology, Guwahati, Assam, India. So here I am going to present my work on ripple improvement and steady state analysis of a boost converter with higher step up ratio. Here is the outline of my work. First there will be an introduction, then circuit configuration of proposed converters, and then some features of the proposed converters, which are ripple in inductor current, ripple in input current, output voltage ripple, simulation results, and then finally an experiment has been conducted. So there will be an experimental setup and experimental results, and in the end there will be conclusion. So, before going to the depth of my talk, I want to introduce the motivation of this work. So, basically, as we know, the conventional boost converter has the voltage conversion ratio of 1 by 1 minus alpha, and the ripple in input current and output voltage is quite high. To reduce this ripple in input current, one can use larger inductance value, but the problem is that it will deteriorate the dynamic performance and it will make the proposed converter more bulkier. So here I'm going to introduce a new type of converter which has the uh, modified voltage conversion ratio, and the ripple in input current, in inductor current, and in output voltage will be less. So therefore the steady state analysis and the voltage conversion ratio of the proposed converter will be discussed in the in the next slides. And the ripple through the inductor currents and will be also discussed, and it will be you can see that the ripple in input current and inductor currents and an output voltage is less than the conventional boost converter. So figure 1 shows the circuit configuration of the proposed ripple input boost converter by using a directly coupled inductor. So first you can see the input voltage is followed by a inductor windings L and then the switch S. So this portion is completely similar to the conventional boost converter. But in the next part, there comes as two identical capacitors C1 and C2, which are placed cross-connected fashion, and D1 and D2, these are the two diodes which are placed in parallel. And you can see here that we have used an extra inductor in the output side. So why we are using this inductor? Basically to oppose the sudden change in output current due to the series parallel transition of these two identical capacitors, we are using this inductor here. So in the figure 2, you can see the magnetic structure of the coupled inductor. Actually, we are using two C-type, or whatever you can say also U-type core, to design the coupled inductor. Uh, Here, the voltage conversion ratio means whatever the voltage conversion ratio we will get, that will not be affected by the coupled inductor, but the diode capacitor will modify that conversion ratio. The main objective of the coupled inductor is to reduce the ripple in inductor current as well as in output voltage, but the diode capacitor cell is modifying the voltage conversion ratio of the proposed converter. So here it comes, the generalized equation of the dual winding coupled inductor, and you can see that we have designed the coupled inductor in directly coupled fashion. So equation 1 and 2, it has been rewritten by the following equations to determine the inductor current in every switching states. So in the next slide we shall talk about the I shall talk about the uh, mm, switching states of the proposed converter. So this is the idealized waveform of the proposed ripple improved boost converter. So you can see during the alpha TS duration, the switch S is on. That time the inductor currents IL and ILF both increase, and off state 1 minus alpha into TS, duration, that time both the inductor current decrease. So and simultaneously other waveforms of the IC, VC, ICF, BCF you can see also. So TS is the total time period here. In the next slide, we shall discuss about the on-state and off-state topology of the proposed converter. So here it comes the on-state on-state circuit configuration of the proposed converter. In this circuit configuration, switch S is on. Therefore, the two diodes D1 and D2 they are will be in reverse bias condition. Therefore, these identical capacitors C1 and C2 they will be in series through the switch S. Therefore, the resultant voltage becomes Vc plus Vc equal to 2Vc. The other voltage and current equations are given as follows. You can see all those equations. Here it comes the next very next duration, which is off state duration. In this duration, switch AC is off. Therefore, the diode D1 and D2 will be in forward bias. The same cross-connected identical capacitors will be in parallel during this period. And you can see that this time these two C1 and C2 they are in parallel. So the voltage and current equations are as follows. You can see those equations here. The output load current equation and output voltage equations are same as the previous circuit configuration. So what will be the voltage conversion ratio of our proposed converter? So that has been determined by voltage second balance equation. You can see the first we have applied the voltage second balance equations for the voltage of inductor L, and in the next duration we have applied that VSB equation for the voltage of LF winding, and then both these equation 13 and 14 are giving us the voltage conversion ratio of the proposed converter, which is V0 by V in equal to 1 plus alpha by 1 minus alpha. You can see that an additional plus alpha terms has appeared in the numerator part of the voltage conversion ratio. That means our voltage conversion ratio is better than the conventional boost converters conversion ratio, which is 1 by 1 minus alpha. So this is the ripple in inductor current. So in this you can see the ripple in inductor current of the L winding is defined by delta L equal to alpha Ts V in by 1 plus K into L. So in the conventional boost converter, this 1 plus K terms will not be there. As we are introducing a new terms 1 plus K here in the denominator, our ripple in inductor current will be less. The ripple in LF winding is also determined by the same way, and it is delta LF equal to alpha Ts V in equal by 1 plus K into LF. So the 1 plus K means the coupling effect is also there. The ripple in output voltage, which is defined by this equation number 22. And in this equation number 22, you can see the delta ILF terms is there. So as the delta ILF already the ripple delta ILF is defined by alpha Ts V in by 1 plus K into alpha. So as the 1 plus K term is in denominator, the output voltage ripple will also be less. So delta V0 can be written by this equation 23. You can see that in that equation 23, 1 plus K terms is in denominator. So the using coupled inductor, output voltage ripple can be reduced. So here it comes the comparison table of the proposed circuit with the existing and conventional boost converter. You can see the proposed boost converter has the conversion ratios of 1 plus alpha by 1 minus alpha into V in, whereas the conventional boost converter has the conversion ratio of 1 by 1 minus alpha V in. So obviously the proposed converter has the better conversion ratio than the conventional boost converter. And the other features are delta L, delta LF and delta V0, in which case in every case there is 1 plus K terms. So you can see that the proposed converter has the less ripple than the conventional boost converter. So here figure 6 shows the voltage conversion ratio with respect to the duty ratio. You can see that the proposed converter's conversion ratio is better than the conventional boost converter. The voltage gain is higher in the proposed converter than the conventional boost converter. So now, by varying the duty ratio alpha, the improvement of current ripple delta L in the L winding is provided in figure 7. So you can see that conventional boost converter is present. Conventional boost converter and the existing boost converters, they have the ripple much higher than the proposed converter. And if you increase the coupling factor from 0.5 to 0.9, so the ripple in the proposed boost converter will be more or less. So more tighter coupling can be used to reduce the ripple in inductor current. Ripple in inductor current. So these are the parameters which have been used to design the converter. You can see the inductance L and LF, they have the equal inductance value 180 microhenry, and the capacitor identical capacitors which are C1 and C1 equal to C2. They are the value of this capacitor are 220 microfarad. So figure 8 shows the ripple in inductor current at 40% duty ratio. Here you can see that if the coupling factor is k equal to 0, I mean we are not using any coupled inductor. Instead of using coupled inductor, we are using two single inductors. That means k equal to 0, and that time the ripple delta LF will be 0.45 ampere. And if you replace that two single inductors by a dual winding coupled inductor, then the ripple is delta L equal to delta L F equal to 0.3 ampere. That means by introducing a coupled inductor, you can reduce the ripple in inductor current. Now the ripple in output voltage. So in these slides also, what you can see that first the coupling factor k equal to 0. That time the output voltage ripple is 97.3 millivolt. When the coupling factor k equal to 0.5, that time the ripple is 64.9 millivolt. So you can understand that the ripple has been reduced by using a coupled inductor. In both cases, the output steady state output voltage is 22.415 volt. That means the mutual inductance doesn't affect the steady state value. So here is the experimental setup of my proposed boost converter with two single inductors. First we have tested with two single inductors. These are the results of the of the proposed converters with two single inductors. Here the ripple delta L equal to 450 milliampere in both cases, and the duty ratio is 40%, alpha equal to 40%. Now in this figure you can see that we have replaced the two single inductors by a dual winding coupled inductor, and that dual winding coupled inductor pictures is given in the right side. So these are the experimental results with coupled inductor. The ripple in IL is delta IL, which is right now is 300 milliampere, and ripple in ILF is delta ILF, which is right now 300 milliampere. Earlier it was 450 milliampere when the coupling factor k equal to 0. Right now, as we are using a coupled inductor, so the ripple has been reduced. The proposed ripple improved boost converter output voltage ripple, you can see here the delta V0 is right now 70 millivolt, which is very similar to the our simulation result, which was 69.74 millivolt kind of. So what we have achieved from this converter? So one thing we must conclude that this converter has a larger step up conversion ratio than the conventional boost converter, and if you use a dual winding coupled inductor, the ripple can be reduced. More tighter coupling you will use, the ripple will be more or less. So, and the coupled inductor reduces the size of the magnetic cores as both the windings of the coupled inductor shares one single core. It reduces cost and bulkiness of the system. The mutual inductance doesn't affect the steady state value of the output voltage. The experimental results are provided to see the physical realizability of the proposed converter. These are my references. Thank you. Thank you very much.